That'll be the next year's class's problem. Well, I don't actually. Next is a slope field problem, 2016. So we're given dy dx. When I see one of these, when I see a dy dx expression, for me, for my own self, what I like to take note is, does it depend on only x, only y, or x and y? So you see here, it depends on y and x. You see that the y is squared, so it, you know, and so on and so forth. But like, just pay attention that it depends on both x and y. Okay, so what we're gonna do is, first you have to sketch a slope field for the differential equation, right? So now, because y is in the numerator, right? You know that if y is 0, the whole thing is 0. So that's the first thing I do, right? So here, y is 0, it's 0. All right. And then the next 2 points, right? So here I have 0, 1. And if I plug it in there, I have 1 over -1, which is -1.
Should you specify? Wait, like you see how you put the points on the left?
And then here, you don't have to do any of that. All they're looking for are your slopes. That's it. All they're looking for is the slopes. And then here, you have 0, 2. And if you plug that in, you're going to get 4 over, how much? -1. So that's going to be -4. That's going to be like this. And here, it's going to be like that. And you know what? This is good enough. So if I just, hang on, if I just erase these are good enough. Okay, so now here's what you get points for this one. You get 1 point for the 0 slopes and 1 point for the non-zero slopes. So if you got these 2 right, that's a point. If you got those 4 right, it's a point. If you got 3 out of 4, it's not right. So that's what you need. Okay, let's move on. Let y equals f of x be the particular solution to the given differential equation with the initial condition f of 2 is equal to 3. Write an equation for the line tangent to the graph of y equals f of x at x equals 2. So we want an equation for the tangent line. The point that we're looking at is 2, 3. And then we need it to approximate f of 2.1. Okay, in order to write an equation of a line, I need a slope and a point. Okay? The slope is dy dx evaluated at 2, 3. And that's going to be 9 over 1, which is 9. So f of x, right? Remember, y minus y1. So f of x is equal to m x minus x1 and then plus 3, right? Plus the y. So remember, it was supposed to be y minus y1 equals mx minus x1, and we just solve it for f of x. So that's the equation of the tangent line. And then f of 2.1 is equal to 9 times 2.1 minus 2 plus 3. 9 times 0.1 plus 3. So that's 0.9 plus 3. And that's just 3.9. And here again, this is not too many points for this one. 1 point for this, 1 point for this.
Oh, that's the one where it was
the linearization or something?
Oh, yeah.
This is the linearization, huh?
Like where it's approximation, right? And not actual.
Oh, like that one?
Oh, they're not too particular about that. They're not too particular about that. If you did this,
yeah,
they'll give it to you either way. They'll give it to you either way. C, find the particular solution to the given differential equation with initial condition this. So here you have to do separation of variables. Okay, so we have dy dx. I am. Is equal to y squared over x minus 1. That, I haven't done anything yet. I've just copied. Separation of variables. We got to get all the y's on one side, all the x's on the other side. So it's going to be dy over y squared is equal to 1 over x minus 1 dx. Okay, you'll get a point for this one. Then antiderivatives. This is y to the minus 2, so it's going to be y to the minus 1, negative, so negative 1 over y, equal to ln of x minus 1 plus c. Let's put in our initial conditions. When x is 2, y is 3, negative 1 over 3 is ln of 1 plus c. ln of 1 is still 0, so c is negative 1/3. So I get negative 1 over y is equal to ln of x minus 1 minus 1/3. And here you need to solve for y. You will not get points, full points for this. All right? So here, this was 1 point. The correct integral or the antiderivatives were 2 points. This is another point, but now there is one other point left, and that's for the correct solution of y. So here's what I'm going to do. Negative 1 over y is equal to 3 ln x minus 1 minus 1 over 3. Okay?
What? Shouldn't you put
I just
ln
did a
of-
common denominator. Just a common denominator.
You should get the ln on the top instead of the bottom.
I don't know.
Shouldn't it be on the bottom?
Should it?
Oh, because she hasn't divided. Sorry.
So now what we're going to do is I'm going to do two things at the same time. Take a reciprocal and make it negative. So y is negative 3 ln x minus 1 plus 1 over 3. No, I didn't switch it. Sorry. 3 over negative 3 ln x minus 1 plus 1. And so you get the last point for that.
Can you just put the negative on the top?
Yeah.
Make it negative?
Okay? All right. So if you do not do separation of variables from the beginning, if you do all sorts of other creative things, it's 0 out of 5 points for this part. Okay? All right. Second to the last one. The inside of a funnel of height 10 inches has circular cross sections as shown in the figure. At height h, the radius of the funnel is given by this equation, where h is from 0 to 10. Units are in inches. Find the average value of the radius of the funnel. All right? Average value, don't confuse this with average rate of change. That's a big mistake. That's a common mistake. Average value is the integral. It's 1 over 10 times the integral from 0 to 10, 1 over 20, 3 plus h squared dh. And this one was a weird one for me just because of how the numbers work. So this is going to be, I'm going to bring the 1 over 20 out, so it's going to be 1 over 200. And then we're going to integrate this. So it's going to be 3h plus h cubed over 3, evaluated from 0 to 10. And now look at this. This is 1 over 200 times. When I put the 10 in here, I get 30 plus 1,000 over 3 and then minus 0. Okay? So if I distribute the 20, I get 3 over 20 plus 10 over 6 if I distribute the 200. And then if you do a common denominator, that's 109 over 60 inches. That's the absolute value. That's the average value. So that's part A. Then part B, we want the volume of the funnel, right? And the volume, how do we find the volume of the funnel? If you have, well, no, we're not going to revolve it because we don't have, what do you call it? We don't have the equation. But what we have is the radius. And then if you think of each one of these as tiny little discs here, if you just see a series of discs, and if I find the volume of one, and then I add it from 0 to 10, if I find the volume of each and every single one of these from 0 to 10 and add them up, that's like an integral, right? So if I were to draw like, you know, an infinite number of discs like this, find the volume of each one, and then add them up. So what is that going to be? It's going to be pi r squared times a tiny little height. That's dh. So this little height here is dh. Okay? So I'm going to do pi r squared dh, pi r squared dh, pi r squared dh, and then add up all of them. That's like doing pi r squared, and then I'm going to add them all. That's the integral from 0 to 10 r dh. Okay? So
R squared.
r squared dh. Like this. So what we have here is pi r squared h, right? And the fact that it's dh and we're integrating, we're adding all of the volumes of all of the tiny little discs. So now, if I square the 1 over 20, I get 1 over 400. And so it'll be pi over 400 times the integral from 0 to 10 of 9 plus 6h squared. I'm foiling basically. H to the 4 dh. Let's integrate this guy. Pi over 400, 9h, plus 6h cubed over 3, which is 2h cubed, plus h to the 5 over 5, from 0 to 10. And so here we get pi over 400. I'm going to go underneath here. Times 90 plus 2,000 plus 100,000 over 5. Okay, so now you can, okay, so I kind of, when I distribute the pi over 400 to the first one, cancel out 1 0, and what do you get? 9 pi over 40. And then what I did, because the numbers were like, there were just way too many zeros, because I got 40 for the first denominator, I was like, you know what, I'm going to get 40 for the other denominators as well. So now, if I distribute to the other one, and I get rid of 1 0, I get 200 pi over 40. You guys see what I'm doing? So just make the denominators 40. And then here, that was how many? 20,000, right?
No, just 2,000 pi.
Yeah, so that was 20,000. Get rid of 1, so you get 2,000 pi over 40. And then all of that together is 2,209 pi over 40. Remember, no calculator for this one. What are the units?
Isn't it over? Oh, wait, never mind.
Inches cubed.
Cubic inches, yes. Okay. Next. Okay. The funnel contains liquid that is draining from the bottom. When you see something draining like this and you're given the radius, that's a related rates problem. At the instant when the height of the liquid is h equals 3 inches, the radius is decreasing at a rate of 1/5 per second. So this is dr dt equal to negative 1/5. At this instant, what is the rate of change of the height of the liquid? So we want dh dt. Okay? So I have dr dt is equal to negative 1/5 when h equals 3, and I need dh dt. Okay, so look at that. Like, I'm lucky here because I'm given r in terms of h, and all I need to do is take a derivative of that, right? So I'm going to take a derivative, though, with respect to time, dr dt, which means this is going to be 1/20 times the derivative of this with respect to t. The derivative of 3 with respect to t is 0. The derivative of h squared with respect to t is 2h dh dt. Okay? This is 1/20. So finally, I have that dr dt is negative 1/5 is equal to 1/20 times 2 times 3 times dh dt. So negative 1/5 is 3/10 dh dt. So dh dt is negative 1/5 times 10/3. And that is equal to negative 2/3. And what are the units?
Inches squared.
I have a height over time, huh? Inch per second. Okay. So dh dt, forget about the d's. It's height over time, inches over seconds. All right. Each part of this was 3 points. And interestingly, here they give you 2 points for the chain rule and 1 for the answer. So it's interesting. It looks like for this one, they didn't allocate points for units, but in another year they may. Okay?
I missed how you got 2h dh dt.
It's the derivative of h squared. What's the derivative of h squared? 2h, but because it's with respect to time.
Yeah, that makes sense.
Yeah. Of course it does. It's math.
How do the points for the other?
Which points?
For like the first 2 parts?
Oh, so 1 point for for writing the correct integral, 1 point for the right derivative, 1 point for the answer. And here, 1 point for the correct integrand, 1 point for the correct antiderivative, and 1 point for the answer. So not much points, right, for these calculations, because that's not a calculus thing.
So could we have simplified before and made it like 8 over 10?
Okay. All right. Look at this. This is becoming a theme, right? The functions f and g have continuous second derivatives. Perfect. The table above gives values of the functions and the derivatives at selected values of x. K is f of g of x, major chain rule happening here. Write an equation for the line tangent to the graph at x equals 3. Again, equation for the tangent, we need a slope and a point, okay? So what we need first is the slope, k prime of x, is f prime of g of x times the derivative of the inside, g prime of x. That right there is the point of this problem. All right? It's them wanting to know, do you know that this is a chain rule? Okay? So now we need this to be at the point 3. So this is f prime of g of 3 times g prime of 3. f prime of, well, g of 3 is 6 times g prime of 3 is 2. And then, these are fun, I love these. F prime of 6, so f prime at x equals 6 is 5. That's equal to 10. Okay. But now, okay, so now I want k of 3, right? Because all this is happening, right? I have my slope, now I need my point. K of 3 is f of g of 3, and that's f of 6, and that is 4. So this is happening at 3, 4. Therefore, it's y equals m x minus x1 plus y. 4. Okay? 2 points for the slope. Oh my. 1 point for the equation of the tangent line. Okay, part B. Let h of x be g over f. What's h prime of 1? Okay, product, quotient rule, right? So h prime of x equals, okay, so remember low d high, take high d low.
I just like to do
So
multiplication.
low, that's fine too. Low d high, take high d low, cross the line and square the low. All this at 1, right? F of 1, g prime of 1, g of 1, f prime of 1 over f of 1 squared. And then all we need to do is look back. So f at 1 is negative 6, right? G prime at 1 is positive 8. So negative 6, positive 8, minus 2, 3 over negative 6 squared. So all that is negative 54 over 36, negative 3 over 2. Two points for this, 1 point for the answer. C.
If you swapped it into an exponent, so it's to -1, then did the derivative of it like to -1?
Yeah, product rule.
Yeah.
You get the same answer.
Okay.
They don't
No,
care.
they
They don't mark. No, they don't mark off. Okay, so now actually the 2 points is not for that, it's for this. Okay. C. C wants the integral from 1 to 3 f double prime of 2x dx. Okay.
Oh, that's the same.
So if you take an integral of a derivative, right? You basically undo one derivative. It's the antiderivative. But if it's a second derivative, then you undo one level and you get f prime. F prime of 2x, but this is u substitution because it's not f prime of x, it's f prime of 2x. So u is equal to 2x, right? And remember, when the derivative of u is a constant, all we need to do is multiply by 1 over 2, right? Or just divide by that constant. Okay? And then all this needs to be evaluated from 1 to 3. So this is going to be 1 over 2. I'm going to take that out. And then look, it's f prime of 2x. So f prime of 6 minus f prime of 2. All right, in parentheses. So this is 1/2. F prime of 6 is 5. F prime of 2 is -2, so 5 plus 2, 7 over 2. 2 points for this, and then 1 point for this. They may give you 1 point. They may give you 1 point for this if you forget the 1/2, but then you wouldn't get the second point here, the last point here. All right, so you'll only get 1 out of 3 points. Or not, I don't know. It depends on the year. Like I said, it depends on how the distribution works. Okay. The rate at which rainwater flows into a pipe is given by R, and that's in cubic feet per hour, from 0 to 8. The pipe is partially blocked, allowing water to drain out the other end of the pipe at a rate modeled by D of T for 0 to 8. There are 30 cubic feet of water at time T equals 0 in the pipe. So how many cubic feet flow into the pipe during the 8-hour interval? So nothing big here, right? So just integrating from 0 to 8, R of T dt. This is all you need to write. You plug it into your calculator and you get the answer. How comfortable are you guys right now into plugging this into your calculator and getting the answer? Are we all okay? So you get 76.570 and then cubic feet, right? This is the amount of water that goes into the pipe in those 8 hours. Yeah.
Because you have to have 3 decimal places, would it be wrong if you wrote like 0.57?
Yeah. Yeah, they won't give you points. They won't give you points. That's absolutely the thing. That's an actual thing. So in here, you have 1 point for saying this and 1 point for the answer here. And if you wrote 0.57, you will not get that second point. All right, so B, is the amount of water in the pipe increasing or decreasing at a time T equals 3? So the amount of water is how much, the rate that's coming in minus the rate that's flowing out at T equals 3. So what we need to look at is R of T minus D of T. But because it's happening at T equals 3, what we want to look at is R of 3, D of 3. So what is the rate coming in at T equals 3? What is the rate draining out at T equals 3? So here we get 5.086. And then this is 5.4. And then we need to say R of 3 minus D of 3, right, is equal to negative 0.3. Now, this is our rate. This is still the rate. And we were told that the rate is given in cubic feet per hour. So this is cubic feet per hour. Okay. So far we have said nothing. We've just written a few words.
Would we round there?
It comes out, you know what, it shouldn't round. Let me see. Sorry, it should be, it's actually negative 0.314. Some years yes, some years no. It depends. You are better off putting units, definitely. Now it says, is the amount of water in the pipe increasing or decreasing? So now we say since R of 3 minus D of 3, so this is the rate of change of the amount of water in the pipe. Since this is less than 0, the amount of water in the pipe is decreasing. Now we want at what time from 0 to 8 is the amount of water in the pipe at a minimum. First of all, lots of things here. Amount of water, that's R of t minus D of t, okay? If I want it to be a minimum, anytime you want anything to be a minimum, you need to take a derivative, set it equal to 0, and find there. Now,
So you subtract them and then you do the derivative when subtracted.
Yes.
Yeah.
No.
No.
No. You're gonna take a. I'll tell you before I lose my train of thought. The fact that it's 0 to 8 closed interval means it's the extreme value theorem. So in that one sentence, half a line, there are 3 important pieces of information that they're testing for. Okay. So we do want. Okay, so listen. So here's what we need to do. We want to know R of t minus D of t. We want to know when this is equal to 0. Because we're already given the rate of change. We already have, this is already the rate of change of the amount of water. So we don't need to take another derivative. Okay? Because that's already the derivative in a sense. So we want to see when that equals to 0. Equaling 0 means they have to be R of t equals D of t. So you have to find the point of intersection. And that's t equals 3.272. Okay?
How do we know that that's not a maximum?
Well, because you don't.
value.
Yeah, you have to do the extreme value
part we
theorem.
could just do on our calculator.
Huh?
The
Yes.
okay.
So now, okay, let's just figure out what it is that we want here, right? So if A of t, so suppose A of t is equal to R of t minus D of t, right? Okay, so what is it that we want here? Like, what is the final amount, right? We want the amount of water in the pipe. So what really we're looking for is A of t to be equal to A of 0 plus the integral from 0 to t R of t minus D of t. That's really what we want to test to see if it's a maximum or a minimum. Okay? Maybe I should do it this way. So R of t minus D of t is the rate at which water in the pipe is changing, right? So this is the rate of change of the amount of water in the pipe, correct? Is everybody, yes? That's the rate of change. So if I want the amount of water in the pipe, I need to integrate that, okay?
But you don't need that.
Yes, you do. This is the amount of water that got into the pipe from 0 to 8. But when we started, there was already 30 units of water in there. So at any given time, I have the initial 30 plus however much got in there.